The third thing we're going to learn about today is regression. So regression and correlation are cousins. Both deal with the relationship between two continuous variables. Both have the same null hypothesis that the relationship between those two variables is zero. And both use t-tests for significance. In that case, the t-statistic is the descriptive statistic, either the correlation, in the case of correlation, or the regression slope, in the case of regression, divided by the standard error of that statistic. And in both cases, the degrees of freedom for the t-distribution that we're comparing our test statistic to is the sample size minus 2, because we have to estimate the means for both of our variables in order to compute our regression or correlation. However, they're not identical. Regression is always hypothesizing a causal relationship. So you always have one variable that is independent. That's the cause. That's something that we determine before we do any measuring. And then another variable that's the dependent variable, and that we can't predict the values beforehand. We have to perform the measurements first, but the actual observed values depend on running the experiment. Regression has units. It's a slope. So if we think that the relationship of supply and price is driven by supply, so as you increase the production of widgets, the cost goes down. So the slope would be in dollars per widget, and it can range from infinity, either negative or positive. Correlation, on the other hand, is a measure of association, two variables that vary in a coordinated way. So it doesn't have units. Any two correlations are comparable. But it's also symmetrical. So you can switch the x and y axes and you'll get the same correlation value and it'll mean the same thing. You can't switch the x and y axes in regression because that would be switching the slope from, in this case, dollars per widget to widgets per dollar. So if you thought that price was driving supply, then it would make sense to switch it, but that's a totally different causal relationship. So here is an example of how we could look at cars and noise in a regression context and a correlation context. So in a regression context, our independent variable is the number of cars. So if we brought 10 cars to a traffic light, or 20, and then a different time we brought 30, and a fourth time we brought 40, and we measured the amount of noise that was present when each of these different numbers of cars was present. So this is independent of our sample because this is the independent variable because we set the values before we ran the experiment. This is the dependent variable because we don't know what the noise is going to be. It depends on actually doing the measurements. And since we controlled the number of cars, if noise went up, then the significant regression would demonstrate that more cars cause more noise. Let's assume that we control things well, right? There's no train going by at one of these or anything like that. Everything else is the same except for a number of cars. With correlation, we would pick a range of times. We'd go to the traffic light, and when it was red, we'd count the number of cars that were stopped and measure the noise. We might indeed find a correlation between the number of cars and the amount of noise, but we would not have controlled the environment, and so we would not be able to decisively say that the number of cars specifically influenced the amount of noise. We could just say that there was evidence for association. But this requires less work, right? You don't have to get 40 different cars multiple times to create measurements. You can just go and passively do it. And so this might be a first step. And then if there's a relationship, then you do the test to see if it's a cause and effect relationship. So they're both valuable, but they have different interpretations. So I'm going to walk through what this says on the next slide, but I have this here so that you can look at it in words as well, written out words. So we have these two variables, x and y, and the black dots are always the same. And this red dot is the mean of x and the mean of y. So we call this the centroid. And it's the same red dot in each time. So if you draw a straight line through here at any angle, or just an angle at random, and measure how far each of these points is from that line, and add up all these distances, that total departure, that total deviation from predicted, right? If this is what we predict and this is what we observe, these, because this slope is too shallow, are going to be bigger than the total here. And this, because the slope is too steep, those red lines, the length of those all add up together is going to be smaller than this one. This regression slope is the place where these lines have the shortest average. So you could also think of it as this is a stick, and these red lines are like stretchy rubber bands, and they can only move vertically. They can only stretch vertically. They can't stretch diagonally or anything like that. And when they're all pulling, this would end up having this slope through this pivot point, because if it's forced to pivot here, and they're only allowed to pull vertically, this is the place where you, would have the least amount of distance here. So the regression slope, that's how it gets calculated, cartoon-wise. Rotate it around, and then where it's the lowest, that's where it's best. So in plain English, we want to rule out the possibility that changing one continuous variable has no effect on the value of the second continuous variable. If there's no relationship between the continuous variables, that's our null hypothesis. When we manipulate individuals to change the independent variable, there will be no predictable change in the dependent variable. However, our research hypothesis is that we think that the value of the independent variable directly influences the value of the dependent variable. So if we manipulate items to have specific values of the independent variable, for each unit we change that independent variable, the dependent variable will change by a predictable amount. So here's the setup. We have one sample with n observations, two continuous variables. We calculate the intercept, which is the expected value of the dependent variable when the independent variable is 0. And the slope, the expected amount of change in the dependent variable for every amount of change in the independent variable. And the probability distribution is a normal distribution around the best fit slope. So our null hypothesis is that the slope is equal to 0. Research hypothesis, the slope is different from 0. The degrees of freedom for the slope has 2, the sample size minus 2. For the intercept, is the sample size minus 1. So we get two test statistics, one to see if the slope is different from 0, and one to see if the line is a horizontal line or not, and the one for the intercept to see if the line goes through the origin 0, 0. So we evaluate it. If the p-value is less than our alpha, we reject the null hypothesis and say that changing the independent variable by 1 unit changes the dependent variable by the slope. And if we say it's a non-significant result, then changing the independent variable has no predictable effect on the dependent variable. So here we have our pretend car data and the amount of noise. And so if we found this significant result, we would say the number of idling cars at the intersection, that's the independent variable, caused, because it's a regression, a significant increase, because we found a significant positive relationship, in the amount of ambient noise. That's our y variable, or dependent variable. And then you write the word slope to tell people you're describing the slope. And you write the words standard error to describe how you're quantifying the uncertainty around that slope. And then you say 3.08 plus 1.03, and it should be decibels per car. That's a typo, because it's a slope, right? And then T sub 17, so we did a T statistic with 17 degrees of freedom. That means we looked at 19 cases where we looked at different cars. And our T statistic is 2.99, which gives us a p-value of 0.004. So here's a summary that you can look over that captures a lot of the details about the regression.